Hi everyone, today I am going to discuss this chapter, that is the second chapter, electric potential and capacitance. First of all, the topic that we are going to discuss about electric potential at a point. Electric potential at a point is defined as the work done in bringing a unit positive test charge from infinity to that point without any acceleration. Suppose there is a point charge here and this is a field region. To bring a unit positive charge, say plus Q naught, I want to bring, we don't know the exact distance, so we treat it as the point is at infinity, the charge is at infinity. To bring this unit positive charge from infinity to that point. Now which is the point? You have to select where you want to bring within the field. Suppose here I want to bring, this is the point P I want to bring. Then the amount of work that we have to do to bring this unit positive charge from infinity to this point, we call it as electrostatic potential at a point. So electrostatic potential, we write it as V. It is the amount of work done to bring a unit positive charge from infinity. We can write as the work done as work done in bringing from infinity. It is a scalar quantity. It is a scalar quantity and its SI unit is joule per coulomb, or we call it as volt. Potential can be positive, it can be negative, it can be even zero, depending upon the work done and the charge that you are bringing. If the work is done by an external force to bring this Q naught, the test charge, from infinity to this point, then the work done will be positive. We write like this, the work done, it will be positive. Whereas if the work is done by electricity or by the electric charge, then it will come out as negative. This is by an external force, this is by electrostatic field. And then the test charge, if it is positive, then it will be positive here, Q naught. And if the test charge is negative, then the sign here will be negative. So even work done, it can be positive as well as negative. Charge also can be positive or it can be negative. Depending upon them, work done and the charge, the potential can be negative or sometimes it can be positive. Its dimensional formula is, electrostatic potential dimensional formula is mL to the power minus 2. This is for work done, and for charge it is ampere into time. Together you can write it as mL to the power minus 3 ampere to the power minus 1. This is the dimensional formula of electrostatic potential. Here, this charge, how you bring at this point, the path does not matter. You can bring like this also, you can bring this way also, you can bring this way also. It does not matter. It only depends upon the position where you are bringing and from where you are bringing. So it is independent of the path it follows. But generally we take to make our study easier, we take it as radially. In a straight line we take towards the charge within the field. This is about your electrostatic potential at a point. Now let us come to the next topic, that is your electric potential difference. Suppose there are many charges, positive charge, this is positive charge, this is suppose negative charge, this is suppose negative charge, this is suppose positive charge. In charge region, if you do some amount of work in bringing the charge from one point to another, suppose a unit charge I want to bring from point say P to point Q. These are both within the field, in the field region. Now from P to Q to bring, how much work do you do in bringing from one point to another point within the field? That gives us the measure of electric potential difference. We write it as V, or suppose we are bringing it from P to Q, so potential difference is from P to Q, then it is the potential, final potential, that is you are bringing at Q, minus the initial potential, that is at P. It is the difference between potential at 2 points, final position and initial position. So final potential minus initial potential will give you the potential difference P to Q, because we are doing the work in bringing the charge from P to Q. In this case also, whether you bring this way or you bring this way, so it does not depend upon the path it follows, it only depends upon the position, from which position to which position you are bringing. That gives us the measurement of potential difference. Here also the potential difference, that is work done from A to B, divided by the unit test charge that you are bringing, gives us the measurement of potential from A to B. Potential difference is also a scalar quantity. Its unit, we write it as SI unit as 1 volt. We write it as volt, the SI unit. And its dimensional formula is also same as that of electrostatic potential at a point, that you wrote M L2 to the power minus 3 ampere to the power minus 1. The dimensional formula also remains the same. But one thing you have to know, the first one, that is electrostatic potential at a point, it is the amount of work done in bringing a unit positive charge from infinity to that point. That point should be within the field, against the electrostatic force, because we know that positive charge they repel. So if we are keeping one positive charge here, and this is the field region, and you are bringing a unit positive charge, test charge from infinity to this point, then these two, they will try to repel each other. So we have to do some work to bring, but we are doing against the electrostatic force of repulsion between the two charges. So in this case also, potential can be positive, it can be a negative depending upon their position. So let us do a numerical and see and get the clear picture of what is potential difference. Let us see one numerical here. If 100 joule of work must be done to move an electric charge of magnitude 4 coulomb from a place A where the potential is minus 10 volt to another place B, that means this 100 joule of work done, when you do the solution, work done from A to B, it is given to you, it's 100 joule. We come to know from here, from a place A where the potential is minus 10 volt to another place B. That means we are bringing from point A to point B. So we are writing it as WAB. It is 100 joule. And let us see the other values. The charge of magnitude 4 coulomb. The charge which we are going to bring is of magnitude 4 coulomb. So your test charge Q0 is 4 coulomb. From a place A where the potential is minus 10 volt. Potential at A is minus 10 volt. To another place B where the potential is V volt. To another place B where the potential is V volt. And from here you are asked to find out the value of V. What is V? Now if we use the formula, we know that potential AB is equal to work done to move the charge from A to B divided by unit test charge. Now you know the value of work done. The potential VAB, as I said earlier, it will be final potential minus initial potential is equal to work done. You can put the value, it's 100 joule, divided by the test charge is 4. Then put the values. VB is V volt minus VA is minus 10 volt, so minus 10 volt is equal to 100 divided by 4. So it will give you V plus 10 equal to 4 2s are 8, 4 5s are 20, so it is 25. So V is equal to 25 minus 10, it will give you 15 volt. So the value of V is 15 volt. Here you can see the application of potential difference. It is the difference in potential between the 2 points. That is final position where you are bringing it minus the initial position from where you brought. So final position minus initial position, or final potential minus initial potential gives us the measurement of potential difference. Now let us define the SI unit of electric potential, that is 1 volt. How do you define it? You can define it using your formula. Potential is equal to work done per bringing a unit positive charge. You can define like this. Potential difference will be called as 1 volt. When 1 joule of work is done in bringing 1 coulomb of charge from one point to another point within an electrostatic field. That gives us the definition of 1 volt. Let us now discuss about electrostatic potential due to a point charge. Suppose you have a point charge here. Let me mark it as Q plus Q. To find out the electrostatic potential due to a point charge, according to the definition, the charge we are going to bring from infinity. Suppose say here it is infinity. We don't know the exact distance. We want to bring that point charge from infinity to this point, say P, lying at a distance R from the source charge. Now the amount of work that is done from infinity to bring this unit test charge up to this point P will give us the measurement of electrostatic potential at a point. Then the point here selected is P. Let us consider, while bringing this unit positive test charge from infinity, there is a point A, say, an intermediate point whose distance you know from the source charge. Let us say it is X. And this unit test charge that we say it is of 1 coulomb. You'll imagine it as 1 coulomb. At this intermediate state, the distance of this 1 coulomb of charge, let us take it as x. The distance we take it as x. Electric field line is going this direction. We know we can give one direction for electric field line. Now let us calculate a small work that is done in bringing the charge from A to B. Let us mark this as dx. The line is along the radial direction. We are bringing it straight. The force experienced by this unit positive charge at point A due to this source charge Q, we can write it as F by using Coulomb's law. F is 1 by 4 pi epsilon naught Q into 1 coulomb of charge we are bringing here, plus 1 coulomb of charge. Distance is x, write it as x square. So you will get like this, F equal to this whole thing. You can take it as K also. So 4 pi epsilon naught Q divided by x square. Now small work that is done to bring a unit test charge from point A to B while moving through a small distance dx. Let me write down here. Small work done in moving or in bringing plus 1 coulomb of charge through a small distance dx is dw is equal to F dot dx, dot product of force and displacement. As you know, work done is dot product of force and displacement, which you can write it as F dx cos theta. And here you know we are bringing towards our left side. So with the direction of electric field, it is making an angle of 180 degree. So theta will be F dx cos 180 degree. Cos 180 degree is equal to minus 1. So you will get this as minus F dx. And if you put the value of force that you found out already, here you have, it will look like this, minus 1 by 4 pi epsilon naught Q by x square dx. Now this is the amount of work done in bringing the charge from A to B. Now let us calculate the total work done in bringing from infinity to this point P. Therefore total work done in bringing plus 1 coulomb of charge from infinity to this point P is at a distance r from this source charge Q. So we'll write it as r. So it will become work done W equal to integration of dw, that is minus 1 by 4 pi epsilon naught Q by x square dx. So this term, the constant term, I am keeping it outside. 1 into Q, you will get Q 4 pi epsilon naught integration of 1 by x square dx. So what will be the integration of 1 by x square dx. Then you will first make it like this, x to the power minus 2 dx. This plus power you will take it up to become minus power. Then you will use your formula x to the power minus 2 plus 1 divided by minus 2 plus 1. It will give us x to the power minus 1 divided by minus 1. It will be equal to minus is there, and this power minus 1, bring it down, it will become 1 by x. It will look like this. Positive power will become, negative power will become positive. So we can write this as q divided by 4 pi epsilon naught minus 1 by x. And what are our limits? That also you will have to see. From infinity to r, from infinity to r, here also from infinity to r, and here also from infinity to r. Then put the limits. This minus into minus will become plus q by 4 pi epsilon naught 1 by x to the power, within the limits infinity to r. This one you can write as q by 4 pi epsilon naught. First put the upper limit 1 by r minus put the lower limit 1 by infinity. And as we all know that 1 by infinity is 0, so this term will not exist. It will become 0. You can multiply these two values, then you can get the work done. W is equal to q by 4 pi epsilon naught into 1 by r. This we write generally as the constant. We keep it separate like this, q divided by r. This work done, the work that we have done to bring the charge from infinity to this point, is a measure of electrostatic potential due to a point charge. So this work done gets stored in the system as potential energy. Measure of electrostatic potential. Therefore, V is equal to work done. We can write it as 1 by 4 pi epsilon naught q divided by r. Like this, you can calculate the potential due to a point charge. Here you have to note it. Electric field intensity is q divided by r square, whereas electric potential is q divided by r. The difference between these two, electrostatic potential and electrostatic or electric intensity, electric field intensity is like this. E, electric field intensity, is inversely proportional to 1 by r squared, whereas electric potential is inversely proportional to 1 by r. So if I plot a graph between them, it will look like this. Suppose this is distance r, and towards my y-axis, suppose I am taking electric potential or electric field intensity E along y-axis. Then both the curves will come down like this. One curve I am drawing this way with dotted line, that is indicating potential. I am drawing dotted line. Inversely proportional to r, it will look like this. Whereas E, the electric field intensity, and distance, if you take it, then it will look somewhat like this. I am drawing a solid line. It will look like this. The solid line is for electric field intensity with respect to distance. So it will look like this. Both of them will coincide at 1 meter distance, and the potential as well as electric field intensity will be 1 volt. They will coincide together. The rest it will look, this is for V and this is for E. Graphically, if you represent, sometimes one more question for example purpose is necessary. Let us do one numerical. A point charge Q is placed at point O, you can see here in the diagram. Is the potential difference VA minus VB positive, negative, or 0? This is the question. If Q is suppose positive, and the second question is when Q is negative. So let us first find out this potential difference VA minus VB. VA, or we can take like this, let this distance be RA, and from here the distance is RB. So we will write down like this, let A be at distance RA from O, and B be at distance RB from O. So the difference in potential, it is VA minus VB. Potential at point A, by using our previous formula, we can write 1 by 4 pi epsilon naught. The charge here is Q divided by distance is RA, and potential at point B will be 1 by 4 pi epsilon naught. Charge is Q divided by distance is RB. So you will get like this, Q divided by 4 pi epsilon naught is common, 1 by RA minus 1 by RB. After getting this, you look these two, RA and RB. A is nearer to O and B is far from O. So we know that we have RA is less than RB. The distance of A from O is less than distance of B from O, that is RB. So if here we are getting the reciprocal, so if I do like this, 1 by RA, reverse, if I reverse it, then it is bigger than 1 by RB. So if you look at this and this bracket term, since 1 by RA is always bigger, then the difference of these two will always give a positive quantity. So here 1 by RA minus 1 by RB is positive. Now as this is positive, this bracket term will not decide whether is the potential difference is positive, negative, or 0. It will not decide. Who will decide is this Q. Q will decide whether this VA minus VB is positive, negative, or 0. If VA minus VB is to be positive, then Q must be positive, that is greater than 0. So one by one you can give the answer here. VA minus VB is positive when Q is greater than 0. It means when Q is positive. And the second one, to get a negative value, VA minus VB is negative when Q is less than 0. That means when Q is negative, then this quantity also will become negative. If Q is positive, this quantity also will become positive. So this bracket factor will not decide. Who will decide? That is Q, because the bracket term is already a positive quantity, since 1 by RA is bigger than 1 by RB. Like 5 minus 2, suppose this is bigger, this is 2 smaller. 5 minus 2 will be plus 3. So this will be positive here according to the diagram. Let us see the electrostatic potential into a system of charges. Suppose you have charges Q1, Q2, Q3, Q4, Q5 up to Qn charges, and you want to find out the electrostatic potential at a point P. Then what you have to do is you have to add up all the potentials. Because of Q1 at point P, I'm writing it as V1 plus because of charge Q2 at a point P, let me write it as V2. Because of charge Q3 at a point P, V3, and so on up to Vn. Here Vn indicates the potential at P due to this charge Qn. Now you know the formula for potential, just you have to simply add it, 1 by 4 pi epsilon naught. Here the charges are because of the first one is Q1 divided by distance. You say like earlier position vector, if you take it, or unit vectors, you take it R1n or 1p from 1 to p. Then here if you take it as R2p, here the unit vector you can take it as R3p. Here the unit vector you can take it as Rnp. Then you can write here as R1p plus Q2 divided by R2p plus, it will go on up to Qn divided by the charge with nth particle, Qn divided by Rnp. This one if you write as a whole, 4 pi epsilon naught summation I starts from 1 up to n Qi by Rip. So this is the representation of electrostatic potential at a point P due to system of charges. And the next topic that we are going to see is to find out the electrostatic potential due to an electric dipole. Let me take one dipole. Suppose this is minus Q and this is plus Q, separated by a distance 2L from each other. Let us take any point, say here, let me take it as P. I want to find the electrostatic potential at point P due to this dipole. This dipole we marked as AB. This is the center of the dipole O. The distance at which I am going to find out the electrostatic potential is, suppose, say R from the center of the dipole. Then here a little bit of geometrical we do. What we do is we draw the perpendicular lines from B on OP, and this line PO by extending we draw another perpendicular line on PO produced. Here it is, must be 90 degree like this. Let us mark this as M and let us mark this as N. Now let us find out the electric potential at point P due to this point A, that is negative charge. So potential at P due to this negative charge minus Q, you can write VA. VA is equal to 1 by 4 pi epsilon naught minus Q divided by charge is minus Q divided by distance AP, distance AP. Likewise, we can find out the potential at point B, at point P due to this charge, positive charge, that is plus Q charge. Let us write this VB. This one will be 1 by 4 pi epsilon naught Q divided by PB. So according to the system of charges, here we have two charges, plus Q and minus Q. The net potential at P, will be the sum of VA and VB. VA and VB is a constant term, 1 by 4 pi epsilon naught. If I take like this, then positive one I am writing first, Q divided by PB minus Q divided by AP. This Q also, if you take it common here, 4 pi epsilon naught 1 by PB minus 1 by AP. Now let us mark this as equation number 1. Now let us find out what is the value of PB and what is the value of AP geometrically from this diagram. And after finding out the value of PB and AP, we will put the values here in equation number 1 and can get the electrostatic potential at point P due to an electric dipole. So let us see how to find PB. PB here it is equivalent to Pn. If I drop one perpendicular here, these two sides will become equal. PB is equal to Pn. And what is Pn? Then you can see here it is PO minus ON. PO minus ON. PO minus ON. Here PO is equal to R. We have taken this point P at a distance R from the center of the dipole. So it is R. And then what is ON? What is ON? Then you can apply your trigonometry and can calculate that this angle, let PO make an angle theta with the dipole, and these two are vertically opposite angles, theta. If this is theta, then this is the base. So ON will be, its length is L. From the center up to point B it is L. So it will be L cos theta. So ON will be L cos theta. Likewise, we can find out this length OM that will be required for finding AP. Let us see how much is AP. AP will be equivalent to PM. PM here it is PO plus OM. PO plus OM. PO is equal to R, and OM here also you can find trigonometric way. This is O to B is L, A to O is also L, and this is forming the base. In this right triangle, this is forming the base. This is 90 degree, this is theta. So here also it will be L cos theta. This O to M is also L cos theta. So I can write this as L cos theta. Now we put the values of PB and AP in equation number 1. Putting the values of PB and AP in equation 1, we will get VP is equal to 1 by 4 pi epsilon naught, Q by 4 pi epsilon naught, 1 by PB. PB is R minus L cos theta plus, this minus 1 by AP. AP is r plus L cos theta. Now this is q divided by 4 pi epsilon naught. We'll take LCM. LCM if you take will be r minus L cos theta into r plus L cos theta. Both the terms will come. R plus L cos theta into 1 is r plus L cos theta, and r minus L cos theta into 1 is r minus L cos theta. But there is a sign minus here, so minus into minus will become here plus. So these two terms will get cancelled. Then you will get here q divided by 4 pi epsilon naught. L cos theta plus L cos theta is 2L cos theta. Downside you get, because it is in the form of a minus b into a plus b. Then this one I will separate the constant term. Q into 2L. Q into 2L gives us a dipole moment P cos theta divided by r square minus L square cos square theta. But for an ideal dipole, as we know that L is very less, these lengths are very less, 2L is very less as compared to R. For an ideal dipole, 2L is very much less as compared to R. Therefore, this term L can be neglected. If L is 0, then this term also will become 0. So ultimately you can write potential at point P due to an electric dipole is 1 by 4 pi epsilon naught P cos theta divided by R square. This is the ultimate expression for an electric field, electrostatic potential at any point on an electric dipole. Here two cases arises. Let us see the special cases. Case 1, when theta or when P lies on the XL line, that means if P is not here making an angle theta, P is somewhere here, suppose, then in that case what will be the expression? In that case, that is theta is equal to 0 degree. This angle theta will become, if it comes like this, P, then theta will become 0 degree. And if theta is equal to 0 degree, then you will get the maximum electrostatic potential 1 by 4 pi epsilon naught P divided by R square is the maximum value, because cos 0 degree is equal to 1. So 1 into P will be P. Like that, case 2, when P lies on the equatorial line, in that case, there is theta is equal to 90 degree. If P lies on the equatorial line like this, then angle theta will become 90 degree. And in that case, the electrostatic potential at point P will be P cos 90 degree is 0. So anything multiplied with 0 will come up to be 0. So it will have minimum value, or we say that there will be no potential, electrostatic potential on the perpendicular line. That's all for now. Please wait for the next video. Thank you.